Billions of people overcrowding the Earth, or billions scattered around in outer space? What's better? We have been destroying the Earth for years. Global warming, climate change, pollution, deforestation, and even the rise of unhinged Karens. The Earth has been suffering. We need to step up our game and protect our dear planet. And what better way to do that than sending people to space? It will help dissipate the damage, and everyone would have at least an acre to themselves. Plus, we have seen it all in sci-fi movies. How hard can it be? Very hard, actually. And we don't even know if it's physically possible, unless there are like 3 people living on Earth. But hey, we live in a world of limitless possibilities. Anything can be done. So let's draw out the details of our plan. We will call it Operation Buy Earth. Where exactly are we going in space? That's a question for another day. Today we will assume that we don't have to find a new home, but we can't stay here. So to figure out if this is doable, we can start with the absolute basics. The energy requirements. It takes about 4 kilojoules of energy to launch just one person into space. That's assuming the person weighs exactly 65 kilograms. Doesn't matter how we do it. Rocket, cannon, space elevator, or a giant cosmic slingshot, we'd still need that much energy to escape Earth's gravity. And it's not just people. We're talking about anything that weighs 65 kilograms. A backpack, a fridge, your overdramatic cat. If it weighs 65 kilograms, it will cost you 4 kilojoules to get it off this planet. Although you might forget it in the next 2 minutes, we will still tell you the science behind it. The energy required to lift something away from Earth is equal to its kinetic energy if it were moving at Earth's escape velocity. Kinetic energy is basically the energy of stuff that's moving, and the faster and heavier the object, the more kinetic energy it has. Now, you might wonder how much 4 gigajoules is. It's about a megawatt hour, which is what your household consumes in electricity in a month or 2. It's the same amount of energy stored in 90 kilograms of gasoline, or a cargo van filled with AA batteries, or the energy you'd get from eating 1,000 cheeseburgers. It's leave Earth behind and never look back energy. Now multiply that by 8 billion and you'd get almost 32 exajoules. That's almost twice the total energy consumption of the entire world in 1 year. A lot, but not impossible. But this is just theory. In practice, everything depends on how we choose to launch ourselves into space. If we are using rockets, it's going to take a lot more. This is because of a fundamental problem with rockets. They have to carry their own fuel. To help illustrate a central problem in space travel, let's return for a moment to those 90 kilograms of gasoline. If we want to launch a 65 kilogram spaceship, we would need to burn around 90 kilograms of fuel. Gasoline carries the same energy per pound as rocket fuel, so let's just go with that. Why? Because we are already familiar with it and it's easier to picture than some fancy science fuel. We load that fuel on board, and now our spaceship weighs 155 kilograms. A 155 kilogram spaceship requires 215 kilograms of fuel. Great, now we will have to add another 125 kilograms of fuel to carry fuel. We will have to add 1.3 kilograms for every kilogram we add, and it would be an infinite loop. But wait, we don't have to carry the fuel all the way up. We burn it as we go, so we get lighter and lighter, which means we need less and less fuel. Bingo, problem solved. Now we don't need to add more fuel to carry the added fuel, but we do need to lift it part way. The formula for how much propellant we need to burn to get moving at a given speed is given by the Chokorovski rocket equation. And if you think the name's weird, wait till you hear the explanation. The change in velocity equals the exhaust velocity multiplied by the natural logarithm of the ratio of the rocket's initial mass, with fuel, to its final mass, without fuel. Thank God it took 7 takes to get that right. What matters here is how fast we want the rocket to go compared to how fast the fuel shoots out. The bigger the difference, the more fuel we need. A lot more. To get off Earth, we need to go about 13 kilometers per second, but our fuel only pushes out at around 4.5 kilometers per second. That means we need about 10 kilograms of fuel for every 1 kilogram of rocket. The bottom line? To overcome Earth's gravity using traditional rocket fuels, a 1-ton craft needs 20 to 50 tons of fuel. Launching all 400 million tons of humanity would therefore require tens of trillions of tons of fuel. And if you don't get it by now, that's a lot. If we were using hydrocarbon-based fuels, it would represent a big chunk of the world's remaining oil reserves. This plan is all well and good for the humans, but what about everything else we need? Food, water, and of course our dear pets. In the US alone, there are probably around 1 million tons of pet dogs. Now, we could leave them behind on Earth, and let's be real, they might end up running things better than we do. And honestly, who wants a bunch of well-fed, highly organized dogs in charge? Not us. Definitely not the cats either. Other than carrying our pets, we would also need fuel to produce all these ships and to transport people to the launch sites, and so on. It's not completely impossible, but it's certainly outside the realm of plausibility. But who said rockets are the only option? We can try climbing into space on a rope, or blowing ourselves off the planet with nuclear weapons, and as much as they sound like the interpretation of our stupid space dreams, these methods have been around since the start of the space age. The first is the space elevator approach. It's a favorite idea of science fiction writers, you know, the people who brought us lightsabers, teleporters, and entire galaxies ruled by people in cloaks. So, what exactly is the space elevator? Imagine tying a really long rope to a satellite that's orbiting the Earth. But not just any orbit. This satellite would be so far out that the spin of the Earth would keep the rope stretched out. You know, centrifugal force and all that. You do remember centrifugal force, right? Right? If not, yeah, just Google it. Now, once that space rope is hanging there like a bungee cord, we could build climbers. The machines that would shimmy their way up to the tether, and no, these wouldn't use rocket fuel because that would defeat the whole purpose. Instead, it would be powered by electricity coming from solar panels, nuclear generators, or whatever other energy source humans have lying around that day. So far, so cool. But here's the catch, and it's a big one. This rope we're talking about, it can't just be made of regular rope, or even super rope, if that's actually a thing. It has to be made of a material that is several times stronger than anything humans have ever built. You'd be wondering, I don't weigh that much, I can use a regular rope, and to that the answer is a firm nope, because even if you are underweight, the stress on the cable would be insane. And to bear that, it needs to be strong. Very strong. So engineers came up with a fancy solution, the carbon nanotubes. In theory, they are incredibly strong and lightweight. In practice, they are hard to work with and not exactly available at your local hardware store. But since we have nano attached to the name, we just know it will work someday. The second idea? Nuclear pulse propulsion. Basically, you throw nukes, aka the nuclear weapons, out the back of your spaceship and ride the shockwave like an action hero. This may sound a little insane, but the point is, it's plausible. The key is a well-designed blast shield that absorbs the force without vaporizing the ship. If engineered properly, each explosion gives the spacecraft a big push, and the ship survives, barely, because the shockwave flies off before it has time to wreck everything. This approach was so solid that back in the 1960s, under the brilliant and slightly bold guidance of physicist Freeman Dyson, the US government actually tried to build one of these monster spaceships. The project was called Project Orion, and the idea was somewhat similar to ours. That is, lifting entire city blocks into orbit. No joke. His son, George Dyson, wrote a book all about it, also called Project Orion. Very original. Anyway, the project was eventually cancelled. Some people were excited about launching humanity into space with a chain of mini-nukes. Others, understandably, were deeply concerned about putting our entire nuclear arsenal in a box, launching it into the atmosphere and blowing it up over and over again. And honestly, the real surprise isn't that it got shut down. The surprise is how far it actually got. So, while launching one person into space is doable, sending all 8 billion of us, that would stretch our resources to the absolute limit, and might just wreck the Earth in the process. In the end, it's a small step for a person, but when you multiply that by humanity, it becomes a giant planet-breaking leap. And as much as we love to complain about living on Earth, we'd rather not blow it up on our way out. That was it for today's video. If you enjoyed it, don't forget to like and share. For more such videos, subscribe to our channel, and we will catch you in the next one, hopefully with some more amazing content.